Thank you, Professor Alok. Good morning, everybody, and welcome to the first session of Professor A.N. Mitra Memorial Meeting and Lecture. I am Usha Kulshrestha from Kirodimal College, Delhi University. So in this session, we have two talks by two distinguished professors. So each speaker will have altogether 30 minutes. So without further delay, let me invite our first speaker, Professor James Berry from Iowa State University, Ames. And he is going to speak on ab initio approach to hadrons and nuclei. So please, Professor James.
Thank you very much, Professor Kulshrestha, and also thank you to the organizers for this honor to speak at the A.N. Mitra Memorial Conference. I had the great pleasure to meet Professor Mitra during a visit to Delhi some years ago and to discuss some of his pioneering work in analytical treatment of hadrons, which was motivating work from my earlier works on in the area that I'll be talking about today. So the basic idea that underlies what we're talking about is that we have a theory called the Standard Model, which we believe contains predictive power for all the fundamental processes that brought the universe to the present time, all the fundamental reactions of hadrons and nuclei, and would be also fundamental to predicting processes, for example, for energy generation in the future. So this is what defines our starting point, or first principles, or ab initio treatment of hadrons and nuclei. If we can succeed in this approach, then we should be able to explain and predict nuclear phenomenon and use any discrepancies that are found between theory and experiment to reveal new physics. That's the ultimate goal here. So just a quick reminder of the background here. The primary story of hadrons and nuclei starts with the QCD Lagrangian and then includes electroweak interactions as well. So there are a number of very well-known approaches that are for non-perturbative treatments, and also you have your standard Feynman covariant perturbation theory. Our particular approach features using Hamiltonian field theory, which actually traces we trace our roots back to the pioneering work of Professor Stan Brodsky and Professor Hans Christian Pauli, and I'm delighted that he'll be also presenting this morning. So basically, the workflow that we talk about is once you start with the Lagrangian, is traced in the standard treatments along the lines that are in this left-hand column here. But I'll be discussing some of those steps in a little more detail, but that's just a quick reminder of the flow of the work that we're talking about. We also trace the roots of what we do back to the pioneering work of Paul Dirac, as summarized in his work in 1949, where he introduced three relativistically consistent treatments of Hamiltonian dynamics. We are most familiar from the textbook physics standpoint of the so-called equal time or instant form, where the starting point is to quantize the system on a fixed time surface, where time is the fourth component or zeroth component of a four vector. What we do is following what's called Dirac's front form, where the starting point is a surface tangent to the light front. And the Hamiltonian in the system is going to evolve the system in so-called light front time, which is a linear combination of two components of the spatial four vector. In this approach, the advantage is that you have, of the 10 total generators of the theory, 7 are kinematic and 3 are dynamic, including the Hamiltonian itself, represented by P minus here. And one of the advertised advantages of this approach is a favorable dispersion relationship that relates the energy to momentum and looks a lot like a non-relativistic kinetic energy relationship, although everything is fully relativistic here. This has some advantages for taking advantage of many of the developments in non-relativistic many-body theory over the past few decades. So we're going to follow that approach. So to summarize what you get from the QCD as well as from the QED Lagrangians, we can draw them in terms of elementary vertices once you picked the light front gauge as your choice. So you have your fermions emitting and absorbing gauge bosons, be they photons or gluons. And you have an instantaneous interaction, so-called instantaneous fermion interaction, and an instantaneous gauge boson interaction coming from the elimination of redundant degrees of freedom. For QCD, you pick up additional vertices, very familiar triple gluon coupling, quartic gluon coupling, and a couple of instantaneous gluon exchanges as well. But in a nutshell, that's it. So the Hamiltonian is completely defined in terms of these vertices as well as the associated kinetic energy terms. So it has a simplicity to it. Of course, everything is in color space and so on. And after that, it comes down to details. How do you actually solve a problem expressed as a Hamiltonian of that form in a non-perturbative scheme? So in the original works of Pauli and Brodsky, they introduced something called discretized light cone quantization, where everything is done in a mesh in momentum space. Together with Stan and other collaborators, in 2010, we introduced basis light front quantization, where fields are expanded in a more general way as linear combinations of destruction and creation operators, where the functions F are rather general and satisfy very simple conditions. And the A's are the usual commutation and anti-commutation, anti-commuting and commuting operators. So the standard conditions that we would invoke for these otherwise arbitrary functions are orthonormality, represented here. And in momentum space, we work with the variables of transverse momentum and light front momentum fraction, or Bjorkane X. So that's the orthonormality condition for these functions. And then there's a completeness relationship as well, where you sum over all possible states of that function space. Now, aside from that, it's very general and arbitrary. Of course, you want to be efficient when you do your computations. So it pays to pick convenient functions. And again, inspired by the work of Professor Mitra, the harmonic oscillator comes to mind as a favored choice. In these coordinates, we would choose a two-dimensional harmonic oscillator function where the quantum numbers are radial quantum number little n and angular momentum projection quantum number m. So those would be the basis functions, which are also familiar to people who work with ADS-QCD. For the longitudinal degrees of freedom, we will pick either the original DLCQ momentum space wave functions, or frequently the Jacobi polynomial basis, a set of Jacobi polynomials multiplied by a convenient factor to manage endpoints. So that all being said, it's good to stand back and ask the question of where do we see the symmetries in the problem? Well, with this set of choices that we've introduced, we can set up our calculations to have a fixed baryon number, a fixed charge, 0 being allowed, 1 for proton space, and so on. Or also, depending on baryon number, you would also be able to do baryon number 0 and mesons with various charges. We also conserve total angular momentum projection, J sub z. So our many parton basis states will have fixed total angular momentum projection J sub z. And as a result of that, any single calculation we do produces all states of the system with total angular momentum greater than or equal to that angular momentum projection. We insist that our many parton states satisfy the Bjorkian sum rule. Each and every basis state satisfies that. And when we work with DLCQs, there's a longitudinal momentum regulator called K, also called the resolution of the system. When we work with the Jacobi basis, there's another condition to satisfy, which is the sum over the individual light front Jacobi variables for all the partons in a single state has to be less than or equal to a cutoff value. So these serve as regulators. On the transverse two-dimensional harmonic oscillator, in order to manage boost invariance, to retain boost invariance, we would have to have our many parton basis states constructed in such a way that the quanta of the oscillator added over all the partons in a single many parton basis function state falls within a cutoff called N max. And these are the regulators that we would like to remove to reach the continuum limit. The continuum limit is removing all regulators. So we work in the internal coordinates defined in this fashion, such that the total transverse momenta of all partons in every many-body and many-parton state is equal to 0. Then in addition, we actually, if you might have noticed this, the basis function space is actually over-complete because it's a single parton basis, but we can manage that by introducing a Lagrange multiplier term, which pushes all states of excited center of mass motion higher up in the spectroscopy and away from the physically interesting states. A couple more symmetries to think about. We work within a global color singlet space, so all many parton states are global color singlets. I've already mentioned the choice of gauge, and there's an optional Fox-based truncation to simplify the calculations to make them more manageable. And this attempts to be a fully complete list of the symmetries that govern the calculations that we're talking about. Now, I'd like to quote from Stan Brodsky the fact that light front wave functions, which we can express in the following way, these are the functions that are the amplitudes of our Fox space states. This is your many parton Fox space state in momentum and helicity space for n partons. You're summing over all the n parton states you care about, and you're integrating over all these internal variables to come up with a hadron with total momentum P, total angular momentum J, and total helicity lambda. So these are the objects of interest to solve for. Their overlaps produce quantities of experimental interest, like parton distribution functions, form factors, and so forth. So we can imagine this overall scheme introduced by Stan, where you start with the most general transverse momentum distributions at the top, which are basically products of light front wave functions. Performing various integrals, you collapse these down to other simpler form factors for more direct comparison with experimental measurements. If you integrate and sum out everything, you come up with some total charges of the system. But along the way, you get very popular things like form factors and parton distribution functions. Again, all this emerging from your solutions and eigenvalue problem, as it'll turn out. Okay, so just jumping forward now. So if I want to describe a meson in this kind of framework, I would start with the valence sector of quark, antiquark, and then I would add various sectors, including gluons. I could have a pure glue sector allowed, multi-quark, multi-antiquark, mixtures of quark, antiquark, and gluons, and so on. Similarly, for a baryon, I would start with the valence sector and then add gluons and quark-antiquark pairs on up the line as far as I can go in practical terms. Now, I advertise nuclear physics, so it's useful to also think about deuterium. Deuterium would start with a valence space of 6 valence quarks, and to which you would add, again, quarks and, quark antiquark pairs, gluons, and so forth, as far up as you can go. Now, that sounds like a nice thing, but there's numerical challenges. The basis spaces that we talk about very quickly achieve dimensions which challenge the largest computers on the planet. So I can look at this a number of ways. If I fix my cutoffs at these values and look at the space and spin degrees of freedom as a function of parton numbers, they increase basically exponentially. So as soon as I get to 7 partons, which are some of the states I've listed up here, so I actually get to 8 here. Here's a 7 parton state. I'm up around dimensions of 10 to the 10th, which would strain even the largest computers on the planet. Another way to look at the calculational challenge is to fix the fix the system, baryon, meson, deuterium, and plot all the Fock sectors that contribute as a function of Nmax, which is set equal to Kmax. And again, an exponential increase appears. This particular plot here characterizes what we call full basis light front quantization, where you keep everything consistent with these regulators. And that's the ideal problem, and that's what we're working towards at the present time. Now, currently, here's an update or status report on where we are. Work in progress, so this is preliminary results. If we take a baryon and include all basis states up through, say, 3 quarks and 3 gluons with various other quark-antiquark pairs included. So you have SU3 flavor for your C quarks, and you have gluon configurations going along with your valence quarks. The total Hamiltonian is actually involving now all vertices that I'd introduced earlier. All vertices of the QCD Hamiltonian and light front gauge will be active in a Hamiltonian written down in this particular Fock space. So that's a very challenging problem. Here's some of the analytical forms. We do have some preliminary results to show. Of course, there are parameters in the theory. There's the masses of the quarks that are involved, and there's the coupling constant. There's a basis space parameter, a couple basis space parameters characterizing the harmonic oscillator's role in the problem. These parameters are fixed to get the mass of the proton to be the physical mass, and the form factors of the proton to be close to the experimental form factors. Everything else is a prediction. So here's a snapshot of what we find for the proton. The valence sector takes about 46.5% of the state, and then all other sectors are spread around all the other sectors in the picture. But the second largest sector, in fact, the largest sector, is the 3 quarks, 1 gluon, which is almost a natural sector to expect to be competing with the 3 quark sector, because that's where your first entrance of an interacting vertex appears. But then much smaller percentages for the others, notably the 2 gluon sector, well, along with the valence sector, has a 5% probability. And we expect that percentage to grow as we add more gluon sectors, as well as the 3 gluon sector will grow as we add, say, the 4 gluon sector. This is just a natural progression. So what we interpret our results to be at this stage is a representation of the proton at some initial scale where these Fock sectors are appropriate to that scale. And the regulators in the problem are the regulators that define the UV and IR cutoffs. A typical type of result you can get would be your parton distribution functions for the down quark, the up quark, and the gluon, behaving more or less as you might expect when multiplied by X. And then you can get the strange, the anti-up and the anti-down from the C-quark distribution. Their PDFs emerge as well. So all these results are emergent from the spectroscopy calculation. Lots of follow-up work will progress from this point, but I want to spend the remaining couple minutes talking more about the corresponding problem in the nuclear physics side of things. So what we view the overall game plan is starting with what I've just been talking about, how you move from quarks and gluons to the baryons and mesons, but then we want to go and do nuclear physics as well. To make this jump will be a number of years in the making, but we expect to see emergent from that with appropriate treatment of chiral symmetry, an effective field theory of protons, neutrons, and pions, similar to what Weinberg introduced. So that should be an emergent prediction of this whole treatment. And just to remind you of what the Feynman effective field theory looks like, you have two nucleon forces which are built out of various chiral orders in perturbation theory by exchanging mesons between nucleon lines. And you go all the way up as far as you care to go in diagrammatic chiral effective field theory expansions. Along the way, you predict 3 nucleon forces and eventually 4 nucleon forces. So everything here can be fixed today in today's world by studying two-body scattering data, nucleon-nucleon scattering data, except for certain so-called low-energy constants, which must come by fitting, say, a binding energy of a 3-body system. But once they're fixed, you have a predictive theory of the version of Feynman's chiral effective field theory. And we have been pursuing this in the low energy ab initio nuclear structure game using the so-called shell model, which again is a Hamiltonian eigenvalue problem where the states are expressed in terms of, in this case, Slater determinants of 3-dimensional harmonic oscillators. 3-dimensional because it's a non-relativistic quantum eigenvalue problem. And I'll skip through this just quickly to save time and point out that again, the model spaces grow exponentially as you increase the complexity of the nucleus you're talking about. The dimensions quickly get up to trillion dimensional sizes beyond the scope of current extreme scale computing. They get even larger if you start putting in 3-body forces and 4-body forces, which are coming from chiral effective field theory. Nevertheless, a lot of progress has been made, and enough results are obtained that one can extrapolate to the infinite matrix limit. And carrying out those calculations with derived chiral effective field theory Hamiltonians has produced what today would be called these green dots for the binding energies of light nuclei from helium-4 up to carbon-12 with uncertainties coming from 3 sources. The numerical uncertainty is actually the smallest, even after extrapolation. The chiral truncation uncertainty is the largest. That's because we only work here up to next to leading order, including 3 nucleon forces. That's our state of the art up to the present time. And this gives beautiful spectroscopy of light nuclei.
Hello.
Yes, you want me to wrap it up? Very good. Beautiful spectroscopy.
5 minutes.
Yeah, and I want to save some time for questions. So I'm going to fast forward now and just say we have calculations now through next to leading order, but they're not complete chiral interaction. They look very good. If we make some other approximations to the interaction, we can use our many-body techniques to, among other things, predict the existence of a tetraneutron, which has recently been confirmed. We can look at exotic systems like the so-called Hoyle state of carbon-12 and see its 3 alpha structure. In a recent Nature Communications paper, we showed that, and so on. But many things lie ahead. Let me just wrap this up by listing overall what I consider some of the most outstanding challenges that in principle, this kind of approach can offer insights into with predictive power. And so, but again, I remind you of the bottom line, which is the ultimate goal, is to make precision tests of this ab initio theory, tracing its roots all the way back to QCD and QED, with high precision experiments to see if we can detect new physics. So it's been my honor to present here at this Mitra Memorial Conference, a testimony to this true giant in the field of theoretical physics. Thank you for your attention. Welcome your attention. Well, welcome your questions.
So please, session is open for question answer.
Professor Haridas, it seems, has a question.
You're muted, Professor Gargi.
Okay. Well, this is an age-old question that in approaches like light front, manifest Lorentz invariance is lost. And you have to, for example, in string theory, in the light cone quantization, to check that the algebra of Lorentz generators is correct requires a lot of work. So what
Yes.
are similar challenges in your approach?
Okay, so the symmetries are the symmetries of the original framework set up by Dirac, and those are, for the most part, respected explicitly in the choice of the many parton basis that we work with. There is a slight breaking of angular momentum symmetry in the problem, and that is systematically restored by going to larger basis spaces and more complete Fock spaces. So we're not worried about it. It's a small amount of breaking. We can quantify it and see it, and we can also see that it's reduced by going to larger basis spaces. All other symmetries are, the dynamical symmetries are more difficult to test, of course, but the kinematic symmetries are all seem to be available to us and respected, except for the rotational one, which is, as I said, systematically improvable. But
My
that's a
second
good question.
is, your whole approach seems to be rather perturbative in spirit. How do you manage to capture things like confinement in this approach?
Okay, so in everything I showed today, there is no confining interaction. In the earlier years, we were using a phenomenological confining term. So right now, what we're doing is we're relying on the gluon dynamics to give rise to confining behavior. Now, in the limited basis space calculations, everything is confined automatically by the choice of the basis space. So we can't make fundamental tests of whether confinement is emerging without going to successively larger basis spaces and successively larger Fock spaces. And that's part of the future agenda. So we actually cannot say at this moment whether or not confinement is present in our is emerging from our calculations.
Thank you very much.
It's too limited. Yeah, thank you for your questions.
Maybe we can take one more question if there is any question.
Yes.
Yes, Professor Alok.
Sorry, I just had a dumb question. Am I right in my understanding that in this this basis light front quantization basis, when you talk about, for example, the beta meson, I saw that it was written as a combination of a QQ bar and a QQ bar G and a GG. So does that mean that you guys make no distinction between a glue ball and a meson?
Correct. That is correct. So in principle, the spectroscopy that we're calculating, which includes a tower of excited states, could be analyzed to see which states are dominated by the pure glue sector, for example. But it would be a fully mixed calculation. Every state would in principle have all Fox sectors involved, but you might be interested in, we would be interested in, as these calculations move forward, in finding out if there are selected states in the spectrum which are heavily dominated by the pure glue sector.
Okay, thank you.
That's right. Yeah, so a postscript to that is we've been concentrating on the baryons at the present time, but there's another part of our group that is working up now on the mesons also. So we may have more to say about that in the coming year or so. It's a good question.
So thank you, Professor James. It seems there are no further questions, so we can move on. So it is now we